So, good afternoon, ladies and gentlemen. It is a pleasure for me to welcome here our today's speaker. It is Petr Sváček from the Czech Technical University in Prague, from the faculty of mechanical engineering. Thank you. And Petr studied at our faculty, and he received a PhD degree here, I think 2002. 2002. Yeah. And since then, he's employed at the Czech Technical University, and he is an expert for finite element methods for fluid structure interaction. And today he will speak on application on finite element method for fluid structure acoustic interactions related to the human phonation process. So please take the floor.
Okay, thank you for introduction, ladies and gentlemen. The title of my talk is as we can hear. I will speak mostly about the research which we did with a group of people consisting of several students and several other colleagues. So first of all, I would like to draw your attention about the physical description of the problem of a human phonation and what problems needs to be addressed. Okay, so how the human voice is created. When speaking, the air flows out of lungs through the glottis part, and the airflow causes the vibrations of vocal folds, which creates the fundamental sound, which is further modified by forming of the vocal tract, larynx, oral cavity, nasal cavities to pronounce individual sounds. So when this research was what I'm going to present here is a research which was conducted with several other people. I would like to mention at least some of them. The main motivations comes from Dr. Jaromír Horáček, who is from Institute of Thermomechanics at Czech Academy of Sciences in Prague, and who provided some basic motivation of the research. And they also have some experimental results available. So previously I have cooperated with Professor Petr, who motivated the numerical methods, the application of numerical methods for this case. We have also cooperation with Petr, who just is specialist in the modeling of acoustics. And the results I'm going to present are results of my previous PhD student Jan Valášek, who is now postdoc at Czech University and also in the Institute of Mathematics at Czech Academy of Sciences, and who is expert in Fluid-Structure-Acoustic interaction. And in particular, I would like to present here works which I conducted with my two students, now master students, which are about to finish their master thesis during the summer. And we continued our cooperation during for 3 years. And we did some implementation of 3D finite element method for acoustic and structural parts here. And let me also mention Karel Vacek, who is from Czech University. Partly this motivation of this research was motivated by cooperation with Jan Špec from Palackého University of Olomouc, who is expert in human phonation, and we wanted to, or we submitted a proposal at Great Agency of the international cooperation between Czech Republic, three institutions, and Michael Dalinger from University of Erlangen, who is specialist in the experimental measurements of things related to the human phonations, and Manfred Kaltenberger from Technical University of Graz, who is expert in the acoustics. Okay. So in this talk, I would like to focus on some things which was rather considered as a preparation work for solution of this project. So first, I would like to start with the motivation of this research and description of the physical description of the problem, and I would like to focus on some difficulties we need to overcome during the approximation. Then I would like to present several simplified models. First of all, is a Fluid-Structure-Acoustic interaction model of voice phonation in 2D. Then I would like to focus on a simplified Fluid-Structure interaction model where vocal folds impact will be considered, and then I will talk about extension to 3D, which is mainly motivated by the project. And I promised Petr I will talk a little bit about variational multiscale method, which is somehow also should be included, but I will mention this only shortly, in this case, because I didn't have much to prepare it more detailed analysis. So let's go back to how this human voice is created. Okay, so maybe I will click on something there. Okay. I will present here mathematical models and numerical approximation of the whole process, and I would like to stress out that all the things are not only mathematically formulated but also implemented in in-house software. Yeah. So. And the motivation why to model such a phenomena is like, first of all, better understanding of voice creation process, because as you will see, it is quite a complex process which consists of fluid structure interaction. Then is also acoustic involved, you have a contact problem involved, and there are some also nonlinearities hidden in the problem. Such a model can be used for description or identification of voice disorders, and the motivation from Institute of Thermomechanics comes from because they want to have some vocal folds replacement, artificial vocal folds replacement. So, okay, so first let's think about the structure component. So here is a finite element model, short abbreviation of this. So this is a model of vocal fold, which consists of several materials, where there is an epithelium on the surface, lamina propria here, ligament here, and muscle over there. So you have usually at this problem linear elasticity models are used, and typically two main frequencies of vibrations are involved in the process, which allows to sometimes to use a reduced order model, and I will also like to talk about it. However, the whole process is a coupled problem, and the main behavior of the vibration is due to the flutter type of instability. So there is no active muscle acting on the vibrations, but the vibration is caused by the flutter instability. So we need to correctly address the problem of structure interaction. The flutter frequency is then obtained as a combination of two fundamental modes. Typically, the two modes are the vertical displacement and kind of rotation. So, or motion up to the right, to the left with rotational are included. Okay, so for the flow description, so in our model we are using so-called hybrid approach, which naturally the airflow is a compressible. So the use of compressible model would be more precise, but it is known that the flow velocities, as in these results, of course, numerical results are not relevant in this case, but there are available measurements, and there are known quantities that say that these flow velocities are maximal like 80 meters per second, where the incompressible fluid model can be used. However, human phonation process, the compressibility is clearly included in the phenomena because the voice creation is a compressible effect. So we would like to use incompressible model, but for some propagation, the compressible effects needs to be taken into account, which is done separately by the acoustic model. Furthermore, I would like to mention that there is some turbulence effect needs to be included, more or less when the jet, which is formed by the constriction here, enters the fluid domain, which causes rotation of lots of vertices. So possibly turbulence needs to be modeled, but the problem of creation of application of the turbulent model is kind of challenging here, because in the subglottal part, which is this one, the flow is mostly laminar, or maybe turbulent layer is developed, possibly, but okay, as the jet enters the domain, lots of vortices are created. So in this case, the application of the standard engineering techniques like Rand's models, Reynolds average based Navier-Stokes equations, this based models are not suitable. Here is some measurements. This is not measurement from the vocal track, but there are lots of experiments available. This was performed by Petr in 2011, I think in Paris, where there was a model of vocal folds, and this is a PIE measurement of the flow velocities, where you can see also the jet entering the fluid domain with lots of vortices located in the fluid domain. So we need to take care of this in our simulations. Okay, to model acoustics, here is again a figure from the computational process. Is just to make clear how this computation is performed. Here, this part is basically our fluid domain, which basically includes the inlet boundary condition, and here we have some outlet boundary conditions, and these parts are the vocal folds, which are being elastic. In this part, but for the acoustics, we use much bigger computational domain, which represents the vocal tract, and which includes the modification of the acoustic signal created by the vibrations of the vocal folds. So this is in the larynx, the voice is created here, but it's modified due to the shape of the vocal tract. What is important is that aeroacoustic sources are important in this case. So I will talk about it a little bit later. So that the fundamental sound is not only created by the vibrations, by the vibrating wall, the sound is created, but also as the, I can go back, as the jet, due to the vibrations of vocal folds, the jet is being closed and open, and the jet is okay. So then this modulation of the jet creates another sound, yeah, and also the vortices. So this is also somehow shown here. What is one of the most complicated thing in this in the modeling is that this is the typical behavior of the vibrations of the vocal folds, which somehow don't know it from the internet, but it's typically what happens there. So we start from number one, where the vocal folds are touching each other, and the channel is closed. But after some time, it opens and air goes through. But after several other iterations, the vocal folds are closed again. This is basically typically the periodical behavior, and as you can see here, 1, 2, 3, 4, 5, maybe 6 even, 6 of 10 or 5 of 10 positions are closed. The vocal folds are closed. So almost 50% of the computations, the vocal folds are closed. What does it mean? Okay, here is some sketch of the computational domain in 2D, because in 3D it's hard to imagine what is happening there. So it means that your computational domain for the fluid is disconnected during the closure of the vocal folds. But still, if you want to compute it, so we still need to go on with the computation. So we need to overcome this difficulty, which will be the second part of my talk. Okay, so we have also, I didn't mention, but we have a coupling of due to kinematic and dynamic boundary coupling conditions. In this case, so kinematic boundary conditions means that the fluid velocity should be equal to structural velocity at the surface of the structure, and dynamic means that the applied hydrodynamical forces are acting on the elastic structure. So I talked about that we should somehow include a model of vocal fold impact. Not only that the vocal folds are impacting each other, which causes the closure of the fluid domain, we also need to somehow include the impact forces in the computations. Okay, I talked about the closing of the fluid domain. There are some other things. I mentioned that there are some non-linearities hidden. One of these is due to the fact that the vocal fold during the phonation is pre-stressed. When you are normally breathing and when you don't talk, so your vocal folds are open, so you can easily breathe. But during the speech, the vocal folds are closed and pre-stressed. So when you are having a pre-stressed structure, so we need to take into care the non-linear model of the elasticity. Okay, I talked about laminar and turbulent airflow, and I talked about the aeroacoustic effects. So let me just introduce some first model of Fluid-Structure-Acoustic interaction. So here we considered the linear elasticity model, which describes the displacement of the elastic structure. We assume only a small displacement, so everything is solved on the reference domain. We have the displacement vector. Rho is the density of the structure, which possibly can be piecewise constant in each subdomain. And tau s is the Cauchy stress tensor. Fs are the volume forces acting on the domain. In the domain. So the fluid stress tensor basically is linearly dependent on the tensor of small deformations computed by this, where X, capital X here, references to the reference domain or material domain. Okay, so this is the model. For the flow model, we are using Navier-Stokes equations without volume force, but as the structure is moving, also the surface of the structure is moving, and also we need to take care of modification or deformation of the structure in the fluid domain. So we are using so-called arbitrary Lagrangian Eulerian form of the Navier-Stokes equations. So we have this form here. If we say that WD, which is the domain velocity, is equal to 0, we have a standard form because this is a time derivative. Yeah, so we have a time derivative of u with respect to t multiplied by the fluid density, convective term, and there is a stress tensor, the divergence of the stress tensor on the right hand side. Okay, so when the domain is moving, so the ALE derivative corresponds to the change with respect to time to the fixed point in the reference mesh, and so we replace the time derivative by this ALE derivative, and for the convective term we modify the convection. This is the price we need to pay. We need to modify the convection term by subtracting of the domain velocity in this convection. And the system is coupled with the divergence constant. Divergence of velocity is equal to 0. Okay, so we have a coupling conditions, which basically consists of the condition on flow velocity, that the flow velocity, and okay, so basically the correct boundary condition is that the flow velocity is equal to the domain velocity, just to overcome the issue possibly caused by if you have moving domain, so you don't want to have on the moving domain, which is a rigid or elastic body, you don't want to have the fluid coming out or inside the structural domain. So we need to somehow set it that the flow velocity is equal to the domain velocity, and the domain velocity on the surface of the vocal port is equal to the time derivative of the displacement, which is at the continuous level, it's the same. But when we are doing numerical approximations, we can possibly, I would like to show that we can possibly have all different values for the domain velocity and for the derivative of the displacement, because we possibly can use different time discretizations for structural model and for the domain velocity. And on the surface, on the same surface, we assume that the forces acting on the Neumann boundary condition for the structure is equal to the forces evaluated from the fluid part. Let me just mention here that here you have capital X, which means we refer to the reference domain. We are applying this force on the reference domain, whereas here we have X, which lives in the deformed domain on the fluid part. Okay, once we have solved for the fluid structure interactions, we can involve acoustic analogies to solve the propagation of sound sources. Basically, we can talk about light sail. We can use, for example, light sail analogy, where there is a distribution pressure, which describes the sound propagations given by the speed of sound value. You have a second derivative of this pressure divided by c by the speed of sound minus Laplace pressure, and on the right hand side there possibly can be the aeroacoustic sources. So typically when we are solving on an acoustic part, we have a 0 on the right hand side, and we are just propagating sounds which create for example, for vibroacoustic, we have a vibration of the structural surface, and we only propagate the signal created at this vibrating part. But in the aeroacoustics, we need to include also some sources. Okay, there is missing partial here. So, so this is the second derivative, mixed derivative of the stress tensor, which is right hill tensor here. And for the case of low Mach numbers, which is our case, this right hill tensor can be approximated by this convective part of this tensor. Okay. We might just mention that for the acoustic also we need to include boundary conditions, and usually the sound hard boundary condition is used on the wall, which means that the acoustics propagation is fully reflected at the surface. Which is in principle Neumann boundary condition, which can be basically used on all the walls. But here we have some representation of the mouth, and the signal goes out to the free space, and we need to somehow, we don't want to reflect the sound waves on this part of the boundary. So in this case, we either use the Sommerfeld boundary condition there in our implementation, and Jan Volášek is also using some software from Manfred Kaltenbacher from Graz, and they are using some method which is which is based on perfectly matched layer, and so then we add the perfectly matched layer there. Okay. So let me just talk about the finite element discretizations. I didn't know how much details I should include in my presentation, so I just only introduce here application of the finite element to the structural part, which basically this correspond. Okay, maybe I can go back. Here. We have a second time derivative times density, which after integration is mass matrix basically times the second derivative of the displacement or representation of displacements, and this corresponds to the stiffness matrix. Okay, so here we have a mass matrix which corresponds to the first term, and the second derivative d now has a different form. It is a vector of displacements at the vertices. Yeah? So apologize for this, but okay, it's suitable not to use other notation. So we have a finite element representation of the displacement. Here is the stiffness matrix. There are some forces, either surface or volume, acting on the structure. So in our case, we usually use only the surface forces from the fluid. And there is some artificially added term which corresponds to the artificially proportional damping term, which is basically taken as a combination of the mass and the stiffness matrix, because it somehow has such nice properties. Because we are talking about the biomechanics, so in biomechanics, the structures are usually highly damped for zero velocity, so the damping is quite large here, and we need to somehow model, because we don't have a physical model of the damping available, so we are using this engineering approach, which combines these two matrices for a damping term. Okay, so we have the structure model. Here on the right hand side, there is a hidden application of the flow force acting on the structure. Next, we saw for the fluid flow model, which basically reformulates the Navier-Stokes equations in a standard way. You multiply by test function, integrate omega using green theorem, and you will obtain the Galerkin formulation, which is written here. Basically, the Galerkin formulation is AUV is equal to LV for all V. But for the case of this of the high Reynolds number, which is the case here, we need to overcome the dominative convections, which basically results in the need of addition of the stabilization term. Here we use two stabilization terms because we have the first one stabilizes the momentum equation, but it somehow increases the weight of the momentum equations in the whole system. So basically, the second term is a additional stabilization of the divergence equation, which means that because divergence of u, the velocity should be equal to 0, it's only written on the left-hand side. Okay, we have both problems, and we would like to solve both of them, but we need to satisfy the boundary conditions, so we are using strongly coupled algorithm. Let me just emphasize that this flow model is, in this case, also nonlinear. So we need to linearize it per every time step. Okay, so I would like to present some results, because I need to focus on some further results. So this is the result of Jan Volášek, where we tested how the aeroelastic response of the vocal fold on the interaction with the airflow. So how this interaction is coming with increasing of the flow velocity. So these flow velocities are chosen in some physiological region where it is known about how much air comes out of the lung to provide a speech. Yeah, so we need to be in some good region, and this corresponds to this region, and we can see the response of at the specified point on the surface, on the top surface of the vocal fold, and you can see that okay, the red signal or the 1.87, you can see that increasing amplitudes of this in terms of the displacements occurs. And so this basically means that the phonation process starts and the vocal fold starts to increase the amplitudes. And the original position of the vocal folds are far away each from other. And when you start to oscillate, so the amplitude start to increase and start to touching each other and start to create the sound. Okay, this is the case A. So he tested, he documented, documented the test case for different velocities. For 1.8, if you decrease your flow velocity, you can see that you will obtain a stable position and no phonation occurs, because it's the amplitude doesn't increase anymore. And but for flow velocity 1.85 meters per second, you will obtain vibrations with no damping, but also no increase of the amplitudes. Okay, here is a result in terms of the flow velocities visualized on this during the period of several time instance, and here you have the same time instance where the pressure value is shown and the magnitude of displacement is shown in the area where the vocal fold is located. Okay, this is the fluid structure interaction process. So we have this result, and okay, so to have it, to couple it with the acoustics, we computed the aeroacoustic sources in the domain, which shows these three figures shows the aeroacoustic sources in the domain. This is then plugged into the wave equation for the pressure distribution, and after that the pressure wave equation is solved, and at the microphone, which is located in the somehow near the mouth, the frequency, the obtained signal is analyzed in frequency domain. And here we use not only the Lighthill analogy, but there are several analogies. I don't remember names exactly. You can see that the Lighthill analogy is somehow overestimating the influence in the low frequencies. And what are important called in the speech creation process is these called formants. These are some fundamental frequencies of the vocal tract. So the signal should somehow the signal should somehow be increased at these formats, whereas decreased otherwise. And you can see 5 formats of the vocal tract, and you can see that the first of 2 are clearly the amplitudes are increased, but for the third format, the Lighthill analogy somehow didn't notice it, and but the other analogies were somehow better, as well as for the 4th and 5th format. Okay, this is the Fluid-Structure-Acoustic interaction process, but what we need to include in the model next. So we can see that the phonation onset, so that the process how to start the phonation can be addressed by the simulation, but we are not able to continue our simulation during the phonation, because during the phonation, if I go back, there is the vibrations, the magnitude of vibrations are increasing, even for it's in 0.5 millimeters, so it's exponentially increasing. And once the gap between the vocal folds is closed, and this computation fails in this case. Okay. So now the question is how to address the vocal fold contact, and we need to address it both in the vocal fold, in the structural model, and on the fluid domain. And the second thing is how to address the nonlinearity. Okay, so I have one figure here, simplified. Now let's switch to the simplified structure interaction model, how to include the impact of vocal folds in the mathematical model. So in this case, we consider the mathematical model of Navier-Stokes equation, again in the ALE method. And for the structural part, we have used only reduced order model with 2 degrees of freedom. So the deformation of this elastic body is considered to be a rigid in fact, and we only consider 2 degrees of freedom, which is described the displacement of the first and the second mass, let's say. And such a system can be written as a system of ordinary differential equations using, for example, this paper, where we have a mass matrix, damping matrix, stiffness matrix. We have some aerodynamic forces acting from the fluid flow on the structure, and we need to include possibly the impact forces acting on the structure, which are mostly zero, but whenever the contacts appear, so we need to include these. Okay. So we will use a finite element method for the fluid flow, which is used on the Galerkin plus UPG streamer of Petr Galerkin, Petr stabilizing, pressure stabilizing Petr Galerkin method. We will use the higher order time discretization for the fluid flow, use higher order method for ordinary differential equations, and we use strongly coupled algorithm. Moreover, because the contact of the vocal folds, we use a nonlinear mesh deformation algorithm. I will mention later. Okay, this is some results just to verify. Okay, if I go back, we started with a reference this. In this reference, they did the interaction of this structural model with a simplified model based on the potential flow theory. Okay, so based on it, they know what should be the magnitude of the flow velocity at which the instability occurs. Here we computed several. For each case, we computed several cases. Here you have like from 0.575 meters per second to this value, and you can see here these computations are aerostatically stable, and here is the Phonation of onset for such a value velocity. So we did it for similarly as the reference paper. We did comparison with the reference paper in dependence on the initially prescribed gap, because the value of this flutter velocity depends on the initial gap between the vocal folds, and we see comparison between the in terms of flutter velocity on the y-axis, and here is a gap in the half gap, and it's a half gap in millimeters from 0.2 to 0.6. Okay, so the lines shows the dependence from the simplified potential flow theory, and the dots, these dots correspond to the lower value shown in this. You can see that we have some difference between the flutter velocity in both. We have a male and female model. Yeah, so it's known that for female, the voice creations, the voice is sharp, or the frequencies are higher. For male, these frequencies are lower. So we consider that they consider two cases we follow that, and you can see that we have a better agreement. And for the female model, the male model is basically parabolic shape, and they use the assumption that for parabolic shape, the separation point as at the end of the parabola. Yeah, so maybe they have some simplifications in that case, which doesn't have to be followed in our model. And so we have some discrepancies, but the trend with increase of the flutter velocity is followed, and in the terms of the pressure difference between the inlet and outlet, we have a good agreement in this case. So we have somehow well-tuned our simplified model compared to the 1D model. So now the question is, what I would like to focus on is the inclusion of the contact in the mathematical model, and it is basically done by including 3 components. The first component is model in the model of the impact forces. Here, because we have a simplified model, we use a Hertz impact forces specified like this. When the contact occurs, we add a force, which is somehow we have a constant which depends on the Young modulus of the structure, and this Hertz force is proportional to the delta to 3.5, where the delta is overlap of the two structures each over other. So this was used again from the paper. The next thing is we need to somehow treat the case when the vocal folds are closing the channel. And the question is what boundary conditions we should prescribe at the inlet. Because we have a model of incompressible flow, and when you close the channel but keep your velocity at the inlet constant, so the pressure will increase to non-physical values. Okay, the other thing was to prescribe the pressure. So when we prescribe pressure, so we will see later what will happen. So, but we somehow succeeded with this modification of the inlet boundary condition written here. Okay, so this corresponds. This corresponds to the formulation of the Navier-Stokes equation. So here, maybe you can identify this term and this term together corresponds to the well-known do-nothing boundary condition. This term follows from the skew-symmetric formulation of the convective term, which basically was introduced, I think, by Bruno Fabry and Rana Herturek later, maybe. So in some slightly different formulation. So this is the nonlinear do-nothing boundary condition, which prevents the vortices leaving the domain to create additional amount of energy going backwards into the domain. So this somehow stabilizes the outlet condition when the vortices are leaving the domain. And okay, what we modified this equation by adding this term. This is somehow motivated by Babushka penalization boundary condition. So basically, this boundary condition, when I say that y is 0 from the right, y goes to 0 from the right, basically I prescribe the required boundary condition. If y0 epsilon goes to infinity, we have the nonlinear do-nothing boundary conditions. In our computation, we choose some epsilon somewhere between these two values, which depends on the model use. And I will show, okay, for the static problem, this is not of much influence, but this is greatly important when we have oscillating parts of the domain here and possibly closing the domain. Somehow can treat the situation, provided that we will suitably choose the constant epsilon. Okay, so to include the contact in the problem, so we need to somehow take the topology changes, the computational domain, and we need to modify a mathematical model in this case. Okay, so let me just show what I said about this boundary conditions. This is the behavior for this case where we prescribe the vibrations of the vocal folds with almost closing the case. We did several cases, but this gives you the idea that if we prescribe the velocity keeps constant. But the pressure goes to non-physical values. I don't think I have the figure here. When you prescribe a fixed pressure at the inlet, you will get vibrating inlet flow velocity. But we using a proper choice of this for this boundary condition, the proper choice of the penalization coefficient, you can see that during the opening phase, we can keep almost constant the inlet velocity, but during the closure of the domain, the flow velocity goes down, which is what we would like to have in our model. Okay, so this is okay. Now let's close the domain. Okay, so this is the component which basically says that if the gap, which is somehow, we have a, let's consider symmetric situation for simplicity. And if your vocal fold is somehow vibrating, and if your gap is under some threshold, which is green line here, if the gap is higher than this value, we do nothing. Basically, compute the same simulation as before. Once we cross the not red line but green line here, so once we cross this green line here, either by this, but it can happen, it will go much farther into the domain. So we somehow modify the geometry. And this is basically shown here, for example, for this case, that basically we say, okay, just make this flat, and we keep the computational domain for fluid connected by adding this cross area to the fluid domain, keeping it still in the undeformed. Yeah. So we modify this, and we okay, this clearly doesn't correspond to the closure of the fluid domain. So in order to force the flow velocities to be zero within the solid domain, we basically add this reaction there, or artificial porosity there, with higher values of alpha, or it can depend even on the acceleration in this case. So we choose alpha being high and B, which makes the flow velocity to be zero. Okay, so now we have a model. Let me just show that this deformation, one needs to take care of a large deformation of the computational domain. So this is the typical, let's say, situation before closing, where still we can compute, we still follow the computation on the deformed mesh. You can see the velocity gradient. This is the colored lines are the magnitude of velocity, and you can see the details in the global area. So we can see that we can still keep the deformation in this case, but when, okay, this is the case when the vocal folds should be closed and the deformation starts to be too much, and it can easily happen when we are using linear elasticity analogy, that we are computing on triangles, for example. So the triangles can basically change its volume to be negative, and this destroys all the computations. So one strategy is remeshing in this situation, but remeshing then creates another possibly errors in the system. So, but we were able to increase the robustness of the algorithm by changing these Lamé constant, which depends on the Young modulus, artificial Young modulus and Poisson ratio. We just modify these values based on the minimal angle of the triangle, increasing the stiffness of the bad triangles, or there is some another criterion Q, which says how much the triangle is deformed. So we modify this. Or the other possibilities we would like to try, but we didn't do it yet, is to use nonlinear elastic model, and which maybe should be somehow even better. Okay, now let's come to this situation, and this is our result for the gap closing, where you can see that here we have repeatedly closing the gap between the vocal folds, and we try to show what happens if we are closing the gap with the flow field. Okay, and this somehow shows what is happening here. Okay, so now from A, B, C, D, E, F, we are starting the closure, and B is fully closed. Here you can see that we have a flow velocity, and the red region corresponds to the artificially added porosity domain, which is only part of this domain here, but fully occupy the region between the vocal folds here. And you can see that the flow velocity, okay, here you have detail about is the glottal area, and here we have flow magnitude. And you can see in the open position, the flow velocity is pretty large, but once the domain is closed, the velocity goes almost to zero. And this is the same situation here. Still, the glottal area is still closed, but once the glottal area is open, the flow accelerates within the domain, and we continue the computations. So we can smoothly go within the simulation in this case. This is the difference when we compute the. We prescribe the same motion for both models, and if you don't use the porosity, this is the flow velocity in the glottal part. You can see even when the glottis should be closed, the flow velocity is pretty large, around 10 meters per second. But using the porosity models, this corresponds to the gap. Using the porosity models, the dotted line corresponds to the gap. Using the porosity models, we can make the flow velocity in the glottal part to be zero. Okay, this is somehow visualized in this colorful fluid dynamics result. You can see that we have still open positions. We start to close the gap, and the flow velocity goes to zero here. And here now we open the space. You can see there is almost zero velocities in this region, but starts to accelerate here. Okay. Okay. If we do the computations, we measure the pressure, the outlet pressure or mean pressure at the outlet, and we do the analysis with respect to the frequency analysis of the system. And you can see in the pressure, there is the fundamental flutter frequency visible, but also higher harmonics are also clearly visible in the systems. Yeah, so which should be the case as we are closing the domain. It should be the case, so which is somehow correct with the results. Okay, I have some slide about the extension to 3D with my students Tomáš Madhan and Petr. We realized during last 2 years, we realized the 3D finite element solver for both acoustic part and for the structure part. It allows to use hexahedral elements, tetrahedral elements, prismatic elements, also pyramids. Why all of these? Because sometimes it's nice to use an unstructured mesh, which means tetrahedral elements. But for example, if you are computing on the brick or on the cube, so it's better to use hexahedral elements. Okay, so we would like to have both hexahedral and tetrahedral, but we need to connect each to other, and in order to connect each to other, so we need to add the prism and pyramids. So I'm numerical mathematics, but for a pyramid, maybe I wasn't aware 2 years ago, or maybe I was aware, but during the implementation process, I found out again that for the pyramidal elements, the polynomial functions are not easy to be constructed. You need to use a rational function here. Yeah. We implemented with Petr, we implemented linear elasticity, and after that nonlinear elasticity, using at the moment only Sandman-Kirchhoff model, which is the simplest one to be implemented, and we analyze the pre-stress vocal fold structure using this code. In both acoustics and vibrational parts, we are able to do static and as well as dynamics approximations. So I didn't have time to prepare all the text for this because I did it with students. I can find it then in the diploma thesis after corrections, of course. Yeah. So, but this is some result of just to show you that this is the using the frequency analysis of the vocal tract. We have found some eigen frequency of the vocal tract being 476 hertz in this case, one of the fundamental frequencies, just to show you that we are able to solve something. This is the result of Petr, which presents a model analysis of eigenmodes of vibrations of the vocal folds. And so we can see basically this is one up and down, and I think this is something like left to right shape. The other one is, the other twos are not. This is maybe like this this way, but the most important is this one and that one. Yeah. Okay, we compared it to the result. He did a lot of work, so I just want to show some of these. Here we have a comparison of this three-dimensional, just to be sure that we are correct at least. So we compare it to the two-dimensional results, and we can see that both shapes as well as the frequencies were pretty similar. And this is the three-dimensional computations in the correct direction. This is two-dimensional result. Yeah. This corresponds well. And last thing he did was the let's say fluid structure interactions, where we considered this the previously mentioned simplified model, 1D model of a potential flow, and from this 1D model of potential flow we took the pressures and we applied it on the structure. And we obtain vibration. This is vibrations in terms of the U, V, and W displacements, which is X, Y, and Z component of the displacements. You can see that we have some vibration, which corresponds again well to the results of what were in the reference. Okay, this is the vibration, which is periodically phenomenal, and this is the vibrations of the vocal fold, which corresponds to the I don't know whether to repeat. Okay, possibly I can close it. Okay. Okay. I hope you are not too tired, because the last part is the operational multi-scape method. So I don't know how much time do I have. And I would like to somehow, so what I did during last half an years is to improve the stabilized method. Somehow we would like to improve some of the stabilized finite element method. So let me just explain in detail how does the stabilized method work first. So we approximate the time derivative, A time derivative, by this backward difference formula third order. We will use here abbreviation just to fit everything in one slide. I will use abbreviation that B is equal to the flow velocity. Okay, here I have flow velocity equal to V, not U. So flow velocity minus the domain velocity. And we have basically Galerkin terms mentioned here. Basically, this term together with the right hand side correspond to the Airy derivative. Here you have a convection term. Here you have a viscosity and pressure terms. And here you have a divergence constraint. Plus possibly some other terms corresponding to boundary conditions. So the idea of the stabilization is to test the original equations by modifying this function. So basically, we consider the Navier-Stokes time discretized Navier-Stokes equations, and we don't test it by this function Z, but we modify it by this function of C. And we add the residual base stabilization. So this is one addition, and the other addition is that we add this diff or graph diff stabilization terms, which basically is again if divergence of U is equal to 0, we are adding nothing to the system. And we can, okay, so we have also in the previous line, you can see that if V satisfies the original equation, So it's also these two terms disappear, and we are returning back to the Galerkin approximations. Okay, so now we have stabilized formulations. We add this term to the left-hand side. We have all the Galerkin, CUPG, and PSPG stabilizations, and we can apply, for example, parallel finite element and so on. Okay, so let me just introduce you shortly idea of the variational multiscale method, which was originally shown on a simplified problem. So I like it also to be shown on the simplified problem. Let's consider some operator L, which corresponds, for example, for convection diffusion, but it can be vector operator. It can correspond to Stokes problem or Osset problem. So we have the operator L applied on U should be equal to F with some Dirichlet or simplicity with some Dirichlet boundary conditions. For finite element problem, we first introduce the bilinear form because it's standard in the finite element problem. So we need to introduce finite element the bilinear form, which is basically for smooth function. You multiply LU by V, use green theorem, which results in the bilinear form P, plus there appears some boundary terms on the surface of small omega. In this case, for the variational multiscale method, we can do it on any subset of the domain omega. And so this is basically this can be basically done for any subdomain, and we will later switch on the finite elements for it in this case. We can also introduce a dual operator, which we will do L star, which basically is related to this bilinear form like this, which is something. Okay. So I didn't mention that I will omit the small omega here if the omega will be the whole omega, the domain omega. Yeah. In that case, if the small omega will become the capital omega, we have the zero test functions, and these two terms disappears. Yeah. Okay. So we have our big formulation of the problem, find U's in some space, such that BUV is equal to FB for all test function B. And okay, let's switch to Galerkin formulations. We approximate the space by VH, and we are now solving for UH such that this is equal to the all test function VH from the test space VH. Okay, this is nothing special, but it is known that in some cases, convection diffusion problem, for example, this method is unstable. Okay, the idea of the variational multiscale method, the basic idea is to decompose the solution U as a UH, which is in the space VH, plus U small scale values U prime, which is from direct sum completion of the VH to the whole space V. So the V is a direct sum of VH plus V star, V prime. Okay, and the core scale problem now is this one, to find to find U, which can be rewritten EUH-VH. We only test by test functions from VH, and we have this formula. Okay. We tested the previous case only by the test functions from the finite elemental or the finite dimensional subspace. And the idea of variational multiscale method is to replace this term by a model of U prime. So we need to model this term in the equations. So if we go back to our definition of this bilinear form, we can use the finite element subspace. We can sum over all elements of the triangle. We can go back to the dual operator, and we can plus we need to add the something on the faces of the elements. And the idea of the variational multiscale method is to model this U prime, and for the model we will use fine scale problems. So basically the same equation where we for V tested VH only, we consider only the V prime here, and we can see we have a problem for this, which basically in the strong form means that we need to solve that operator L on the U prime is equal to the residual given by the UH. Yeah. And the advantage is that this can be done locally on each element. Yeah. So, but okay, so we need to solve this problem locally on each element. Here is the local residual of the UH on the element K, and they call it like using the orthogonal projection to separate scale models. We basically approximate the operator L by some operator to take tau K minus 1, which is basically matrix operator, which basically gives you the model to be used for the variational multi-scale method. Okay, so then we tested it, we obtained this for the 3 degrees of freedom. There are some computations. The computations work also for high Reynolds number. And in fact, it is also, in this case, it can be also considered as a kind of stabilization. Okay, I think I ran out of the time, and so I presented the model of fluid-structure-acoustic interactions. I introduced it, how it can be, how to the model can be included some important phenomena as a vocal fold impact, and how to include nonlinearities as pre-stressed vocal fold in the system. So thank you for your attention, and I'm looking forward to